So, hi everyone. My name is Sonya. I lead the personalization team at Outbrain's recommendations group. And today I'm going to talk to you about our recommender system, and specifically two different layers of our recommender system. So the first layer would be our offline layer, our offline modeling layer, which works on top of Spark. And the second one will be the serving stack, the serving layer, which is run on top of Elasticsearch. So, really quick introduction on Outbrain. Many of you probably heard of the company. Basically, Outbrain focuses on discovery. What we do is help readers to discover content that is interesting and relevant to them. And this is how it looks like. So if you are reading an article, let's say on CNN, you're reading a story, you got to the bottom of the story and you're seeing our widget. And our widget has two types of recommendations. First type, we're calling them organic recommendations. So these are basically links that lead you to other articles within CNN. The second type are the promoted stories. So these are links that are taking you outside of CNN, outside of the current publisher. And this could be leading you to sites of other publishers that just want to draw audience to their sites, or it can lead you to marketers or brands that have content on a new product that they're marketing. Okay, so we have offices in 14 locations. Many websites and apps display our recommendations. And these are the numbers which, they are important for us in terms of, machine learning engineers. So we are serving 275 billion recommendations a month, and we're reaching about 1 billion users. And we will get back to those numbers once we talk about the infrastructure. Okay, so before we dive into the system itself, let's talk about our data. What kind of data we're using, and first and foremost, we want to know our users. We want to get to know the users so that we can recommend relevant content to these users. And essentially, the way we know these users is by looking at what articles they're reading, what content they are consuming. Okay. So this means that we need to fully understand what's happening within this content. So basically, it all starts with our NLP engine. Okay, what that means is that we're taking articles, and these are, we're getting documents from all the articles where our widget is being displayed. Okay, this is the first type of documents that we're analyzing, and the second type are all the articles which are our potential recommendations. Okay, we need to understand both of these types of content. So what we're doing is we're crawling them and applying NLP techniques to extract features. And our features, we have different levels of granularity of semantic features. So as you can see, these are 3 examples of features that we are using. We have a more abstract layer of categories, so it's about 100 categories. This is like the high-level classification that we're doing. Then we have topics, which are a bit more specific. And we also have very specific entities. So these are, specific people or specific organizations. So these are the kind of features we're extracting. So here you can see an example, an article on Big Bang Theory, and we have, it was classified to entertainment, on television, something more specific is a sitcom, and specific entities. We have CBS, Mayan Bialik, so you can recognize those. Okay, so we have information on each and every one of our articles. Now, what are we doing with that? We're getting a user. We have the patterns of what this user has been reading in the past, and what we're basically doing is aggregating all this information into one user profile. So you can see it as, in a sense, this user profile is represented in the same feature space as each one of our articles, right? So each user profile has a category, has a topic, has a list of categories, a list of topics, a list of entities, and so forth. So here's an example of a user in the system that happened to read a lot about television and investing and music. So this is the aggregated profile. And if you would have looked at my profile last spring, this is what you would have seen. So I don't know if you recognize these entities and categories. How many of you haven't watched the royal wedding or are ashamed to admit they had? Haven't watched or ashamed to admit? Okay, so speaking about being ashamed to admit we're consuming certain content or watching certain YouTubes, this is something I wanted to share with you. This is a research two of our researchers have conducted several years ago, Ramashuram and Roy Sasson. And what they wanted to check is whether there is any gap between the things that we read about versus the things that we share. And they kind of wanted to evaluate what is the value of the data our brain has versus your Facebook friends or social media. So they analyzed a lot of publishers, they took a lot of page views, and they took a lot of Facebook shares. And what they came up with is these results. So basically you have two types of topics. You have topics that we tend to read about, but we don't usually share. And we have topics that we tend to share, but we kind of rarely read about. And you can guess which one is which. So this is to emphasize the value of the data that we have based on this very implicit interests of the users. Okay, so we've talked about the data. Let's talk about our models. We basically have two types of predictive models. One is content-based models. It means that we are representing. So we talked about the user. We have a profile. We have the interests of the user. And these kind of models, they tend to recommend content which is semantically similar to what our users are interested in. Okay, so if I am interested in music or in technology and travel, these kind of algorithms will probably recommend things related to those topics, and these are the content-based models. And the other type of predictive models are collaborative models you're all familiar with. Probably each one familiar with at least one, two, algorithm types that generate these kind of models. But essentially, as we all know, this is the basic concept of this type of models is that if my taste matches someone else's taste, probably the things that they will like will interest me as well. And we are using three types of algorithms for these: matrix factorization machines, and embeddings using deep learning. Okay, and just to formulate, before I dive into the infrastructural stuff, just to formulate our machine learning challenge. So what we have is basically, on one side we have the features, the feature vectors, and this consists of two types of features. We have the user, and we have the context. And by context, I mean what is the exact article the user is currently reading. Okay, it's very important. To the prediction, it could be what platform the user is using, whether it's mobile or desktop, what time is it, what day of the week it is. So this is the context, right? And we have the user interest. So these are the features. And on the labeling side, we have all the recommendations that we served in the past and whether there was a click or not. So it's a binary prediction problem. Okay, so questions? Okay, so the question is how the texts are labeled. We have an in-house NLP engine that actually extracts all these features. Every team that's doing it. Okay, so let's talk about offline data processing. So I said that I'm going to cover two layers, the offline layer and the serving layer. So we'll start with the offline one. Okay, so a couple of months ago, I bumped into this YouTube, and it's by D. Scully from Google, and a recommended one, by the way. So he was talking about machine learning technical debt. And what he was saying is that essentially machine learning systems are very complex in terms of engineering, not only on the algorithmic level. And often they're even more complex with other back-end systems. And there are certain concepts that we need to make sure they're happening so that our systems are robust. And this is not always the case. And I wanted to show you two slides that I really liked from here, and they're kind of motivation for what we're doing. So this is the first slide. The first slide is you have the cool part of machine learning, and this is the part where you actually write the code of the algorithm, and you do hyperparameter tuning, and you do your own cost function, and you're, changing the algorithm that you downloaded from somewhere, and this is the really fun stuff that we all like doing. But this is a very small part of what's happening. Okay, right? This is a very small square of what's going on. But actually, we have the rest of machine learning here. And the rest of machine learning is all the engineering stuff around it, all these components which are pretty boring, but they're necessary. We have data collection, feature extraction, configuration, monitoring, deployment, and so forth. And it turns out that about 90% of the time of machine learning engineers, data scientists, is actually around these parts and not the core part of theoretically improving my algorithm. And what our machine learning framework it attempts to do is to reduce the cost of these parts. Okay, so as you'll see in a minute. So just to give you a few examples of why this is taking 90% of our time. So I listed out in what we have are really tough tasks. So let's talk about data collection, right? Data preparation. So I guess most of you can relate to those things, right? First, we have multiple data stores. Okay, at Algorithmic we have Hive, MySQL, Cassandra. Secondly, we have everything in different tables because we have different types of events, and these events are going through different flows and are written to different places. So in our case, we have recommendations, then we have clicks, we have user profiles. Each one of these type of events is written to a different place, and we need to somehow aggregate them. We have logic that we need to apply, usually deduping, siloing, stuff that everyone needs, but everyone needs to implement. And all this happens at scale, so this means that it takes a lot of time to run this query. So the complexity is twofold. First, we need to really work hard to implement those stuff. And secondly, when we already implement them, it takes a lot of time to run just to generate a single data set. And we want to reduce this cost. Okay, and another example, so this was data collection. I think I convinced you that it's pretty complex and time-consuming. Evaluation metrics. So this is a snapshot of a model that does evaluation for, summarizes the evaluation metrics for what we're doing. And, we have like more than 15 of those. You have stuff which are classical machine learning, MSC, AUC. You have stuff which are related to ranking in our case, like more a ranking, like MRR. And we have stuff related to business, where we need to take into account the monetization of what we're getting. So there are a lot of metrics, and implementing this is costly. Okay, so this is why we came to a conclusion that we need to develop some framework, and basically we had two goals in mind. The first was we want to perform agile research. Okay, we want to focus on modeling and enabling quick POC. And the second one is that we want to have a robust productization mechanism, and this is so you want to have it in two different dimensions. One is that we want to be able to refresh our models automatically. We want to simplify the way we deploy models, and secondly, we want to make this process safe. And I will talk about it in a second. So how do you make sure that your production environment is not corrupted? Okay, so we chose to use Spark. It's fast, it's distributed. All our information is on Hadoop clusters. Actually, it's Mopar. We have Spark on top of that, and then we have this applicational layer where we implemented the framework, the machine learning framework. And this framework is basically composed out of 5 components. So none of these are surprising. But the thing is that they are decoupled. That's the important thing. And so we have data collection, feature engineering, model training, offline evaluation, and model deployment component there. And the way it serves us in terms of the 2 goals that we've defined is that, so agile research, it enables us to get models in very quickly. The reason is that essentially what we need to re-implement whenever we introduce a new model is
only 2 components, and usually it's only the third one. It's only the model training. We don't even need to touch the feature extraction part. And everything else is out of the box. And obviously, as you can see, data collection and offline evaluation are things which are independent of your model, right? So when a new, a machine learning engineer wants to implement a new model, the way to do it is basically implement 2 functions, and all the rest is ready for for running the job. So we have the add columns. Basically, it means that we are selecting the data that we want to use, and we have the actual logic of the algorithm that we are implementing. And the next stage, after implementing these parts, are just running the Spark job, getting the data collection for free, getting the evaluation for free. That's it. Okay. So, and second goal was the deployment part. So this is why this 5th component is for. And basically, what we wanted to do is use the same, use the same framework to both run it in research and ad hoc, and both run it in production. Okay, so we have an in-house scheduler that just basically runs the same code, but in a scheduled manner. Regardless of what model you might be using, you do want to refresh that upon your data, right? Whether it's every 5 minutes or every 2 weeks. But it's something that you want to have automatically done for you. So we have the scheduler, and it actually runs the same code that we were using in research. And this last part, the model deployment, not only it places the models in production, but it also takes the output of the offline evaluation component and sees whether this model is good enough, whether this model, doesn't ruin anything, it still, brings the lifts that we expect it to bring before it is being deployed and, potentially harms our production environment. Okay, questions before we move to the serving layer? Exactly. So the monitoring, the question was about monitoring the models. So there are two checkpoints. First is before we even deploy the new model, we want to check it on offline data and make sure that it's, it's comparable with our previous results, and that, it brings the metrics are, high enough value. And the second thing, after it is deployed, we have monitoring obviously on the online system and how it actually performs, because you probably know that offline metrics are really nice, but they don't always predict what's happening online. So it's really important to have this both safeguard layers. So moving on to the serving layer. Okay, so remember the numbers from the second slide that I've showed you with the throughput. So if you do this quick calculation per month, this is per second. So this is the throughput. We have 35K requests per second that we need to handle, like recommendation requests. And we need to meet a very strict latency requirement, which is 30 milliseconds. And the reason is that, when someone opens some article on CNN, they expect to see our recommendations right away. So we need to meet this requirement. And the third challenge that we have is that our inventory is is large. We have several millions of potential recommendations from which we need to choose the best ones. So this is a pretty challenging, engineering task of how to tackle it. And what we did is we turned to a different domain. And in a sense, in this different domain, many of these problems are already solved, and I'll show you how we've done the reduction between the two. So we're using search technologies, we're using Elasticsearch, and just a brief overview of why distributed search engines are good for what we're trying to do. So first of all, the main thing that search engines know how to do is getting a query and ranking documents as in terms of their relevance to this query, right? This is like the main thing search engine can do. In terms of the distributed part of search engines, they are distributed in two types of dimensions. So one is that we're able to scale in terms of inventory size, right? We're just adding nodes to Elasticsearch, not getting into the details of how Elasticsearch works, but it's basically you increasing your cluster and you're able to handle a larger inventory. This is one thing. And the second thing is that, as your throughput
goes higher, you can again extend your cluster. You just add more machines and it's scalable. Okay, so these are the advantages, and these are like the key points that made us turn to this direction. Just a quick overview of what makes search engine efficient. Probably those of you who had some connection to search knows these 2 slides will be kind of boring, but essentially what makes them efficient is that when we index some document into a search engine, they create an inverted index. They're not indexed as is, but they invert the terms. And what's happening is that we have a record paired term, and for each record, the key is the term, and the values are the documents where the key appears. And then when we're getting the query, then it's very simple and efficient to just locate all the records that are relevant to this query. And then search engine does 2 things. Very quickly eliminates, filters out stuff that don't contain the terms at all. So this is like the majority of the inventory just goes away. Among the ones that are relevant, it applies a heuristic on the scoring. What is more relevant, what is less relevant. And it usually has to do with stuff like the number of times a term appears in the document, how popular is this term. So there are kind of several heuristics that are being used. Okay, so this is like a classical search engine. Now, in our case, we are we're reducing our problem to a search problem, and we're doing it in the following way. So. We're indexing our documents, we're indexing all our inventory into Elasticsearch, but instead of indexing the terms, instead of using DAG of words, we are indexing the features. Okay, so these are the terms that we're using. We're converting words we're representing all our documents with features. So if you look at the inverted index, you would see, as keys, you would see the semantic features that I talked about here before, like that we have the entities, the categories, the topics. You will see those here. And then the second reduction that we're doing is on the query side. So what's happening on the query side is that we're getting a user, and we're representing this user through the profile, right? Through the features of this profile. Now, if you remember, the way we actually build the profile is making sure that it is the same feature space. We're representing them within this. It's the same set of categories, it's the same set of topics, the same set of entities. Okay, so they're speaking the same language, just as queries and documents. And and then search engine just retrieves the most relevant ones for us. Now, what I've just described is a very, very simple, ranking scenario, and it correlates with the content-based models that I mentioned before. But what we usually use are more complicated models, right? That's what we have this offline model framework for that I described before. So we're using embeddings, or we're using regressions, and these are stuff that cannot be really represented within the simple heuristic of a search engine. So the way we actually incorporate these models into the serving stack is by using Elasticsearch plugins. So I don't know if whoever knows Elasticsearch is probably aware of the feature, but what plugins enable you to do is to write your own scoring function, basically. Okay, so you write your own scoring function in native Java, you deploy this across your cluster, you instruct Elasticsearch to use that one instead of the original one. And you can do whatever you want there, basically. Of course, you are limited in terms of efficiency. You need to be very efficient in your code, because this code will be run for each and every one of potential documents that is going to be considered, right, for your query. So there is a challenge of writing this in an efficient manner, but it does enable us to incorporate, any model that we want into this stack of Elasticsearch. Okay, so this is last slide. Key takeaways. Takeaway number one: do invest in your machine learning pipeline.
It will make your research, more agile, and as you've seen and as you know, it will, we have a lot of overhead in terms of all the components that we're using, and we want to reduce that. So for that, do invest time in the pipeline. Automate periodic model deployment. This is something that will help you to be more agile in deploying new models. Have control mechanisms, not to ruin your production. And if possible, be creative in terms of looking for solution in different domains, just like we did in terms of the reduction from recommender systems to search. Okay, that's it. Thank you. Any questions? Yes.
How do you deal with cold start problems?
With cold start problems. So yeah, this is it's a huge topic. I don't know if I can answer in one sentence, but yeah, so it depends. I mean, on the inventory side, we have information which is not dependent on whether we actually served or tried this recommendation before, because we have an engine that actually tells us what this article is about. So this really helps us to understand that even before we've tried it out. On the user level, if this is the first time we're seeing a user, we will probably mostly use its context. We don't have any information about what they like or don't like. So we will focus on what they are seeing right now, which is a very strong signal, obviously. Okay, thank you.